Mathematics is a very good career to be a human person in, if that makes sense. I think there's a stereotype that you're shutting yourself up in an office and working frantically 20 hours a day and so on, and it's just does not have to be true. It's a career that can involve a lot of flexibility, right? It can involve a lot of travel, and all of that. You have to be willing to move, okay? But a lot of that is stuff that I think people find really valuable right now in terms of trying to balance work and life.
Hello and welcome to Voices of Mathematics, the podcast from the Mathematics faculty at the University of Cambridge. I'm Marianne Freiberger.
And I'm Rachel Thomas, and we're from the Outreach and Communications team here. The person you just heard is Holly Krieger, who is Professor of Mathematics at the Department of Pure Mathematics and Mathematical Statistics, also known as DUPMS. And Holly was explaining why it's great to be a mathematician. So Holly's also a Caulfield Fellow at the Murray Edwards College here in Cambridge, and she's well known for her appearance on the Numberphile YouTube channel, those amazing videos about maths produced by Brady Haran. Holly recently gave a colloquium here at DUPMS, and these are talks that happen once a term that are aimed at all the pure mathematicians here. Now, there's a lot of pure mathematicians here, and they work in lots of different areas.
Yeah, and that makes these colloquia quite special because it's a bit of an honor to be asked to give one, because people think you've got something to say that interests everyone. And you need to think quite hard to make sure that what you're saying is actually accessible to everyone in your audience.
So Holly is the latest colloquium speaker and otherwise a very impressive member of DUPMS. She's won some very prestigious prizes. So we decided to catch up with her. Marianne, you got a chance to talk to her.
Yeah, and later on in this podcast, she will tell us more about her appearances on Numberphile and what it's like working at the faculty, and also what advice she has for young mathematicians. But first, we find out about her work, which is in the overlap of number theory and complex dynamics. I asked Holly what drew her to these areas, and she had quite a surprising answer.
So I don't know if this is sort of an expected answer, but actually what I liked most about these areas, which I sort of started specializing in graduate school, which is normal, was the people that work in them. So I had in fact started in a different area of mathematics, which will go unnamed. Did not, after my first couple of conferences that I attended, see myself working with that group of people well for the next 5 or 6 decades. And so I branched out a little bit, and I found essentially a friendlier group of mathematicians that really were more inspiring to me as colleagues. And so that's how I ended up in these fields. I mean, that was a while ago. Of course, since then I've gone in directions that I find mathematically interesting as well. But even now still, like the problems I work on are very influenced by the people I collaborate with. And that's really a choice that comes down to like working personality and how we're able to communicate together.
And so it's interesting because somebody else recently said to me when I asked them what their advice would be for young mathematician, and they said, be aware that it's not just the area of maths, but the people you work with, you'll be stuck with them for life.
Yeah, that's right.
So what is it about the people that, about that community that makes it?
It's a good question. I mean, so it really depends on a few different things. So one thing is that arithmetic dynamics, which is sort of the intersection of these two fields, is a pretty young field. So significant work in the field was sort of founded by mathematician Joe Silverman. And this was only about 30-ish years ago. And so a lot of the people in the field are younger. So that's helpful. I think also this is something where a small number of people can make a difference, that, with 3 or 4 senior people in the field who have attitudes that are very much positive and interested in interacting with younger people in the field. And I think it comes down to a small handful of people who are really the leaders in the field being people who are very pleasant to talk mathematics to and very, very nice to work with.
Oh, that's really interesting. I think one of the things people don't realize about working in mathematics is that it's very much a job about working with other people and the importance of who you work with and how you work with them. But of course, what also attracts mathematicians to their job is the mathematics. You said Holly works in the intersection of number theory and complex dynamics.
Yeah, she does, and she'll explain more about this in a minute. But first, just for a little bit of preparation, number theory is what the name suggests, is the study of numbers. And it's famous for problems that are quite easy to state, but then really, really difficult to actually prove. So there's a very famous example, which Holly will mention, and it's called Fermat's last theorem. Rachel, you want to remind us of what that says?
Of course. So one way to get a picture of it is if you think of a right-angled triangle, then we know that the square of one side x squared plus y squared equals the square of the hypotenuse. And there's lots of examples of right-angled triangles where the length of those sides are all integers. So for example, you can have 3 squared plus 4 squared equals 5 squared. Now, imagine you slightly, like mathematicians do, you generalize things. And rather than thinking of what integers satisfy x squared plus y squared equals z squared, you say what integers satisfy x cubed plus y cubed equals z cubed, or x to the fourth plus y to the fourth equals z to the fourth, or raising it to any positive integer power. Can you still find the integer numbers, whole numbers, x, y, and z that satisfy that? And now what's interesting is the answer is no. And Pierre de Fermat wrote this, mathematician Pierre de Fermat wrote this. He wrote that in a margin of a textbook and said he had a marvelous proof, but actually it took around 350 years to prove that. And it was announced here in Cambridge by Andrew Wiles in 1993.
Right, that's right. So Fermat's last theorem is a theorem in number theory, because it involves the question whether numbers satisfy an equation. And you've just explained it really, really quickly, but the proof was hundreds of years in the making, and that's very typical of number theory. So that's number theory. Can you tell us a little bit about complex dynamics too?
Okay, I definitely will, but I will be very vague so that we can go back to Holly. So complex dynamics involves complex numbers, which are those numbers you might have heard of that have a real part and an imaginary part. So you have x plus iy, and that means you can think of a complex number as points in a two-dimensional plane. A complex function is a mathematical expression which takes each point from the plane to some other point in the plane. And if you apply that function again and again and again, you can track the trajectory that any given point takes as it gets taken to another point and then another point by the function. That's called a dynamical system because things move, they're dynamic. So complex dynamics is what gives rise to some very famous and very beautiful fractals, such as the Mandelbrot set and also the Julia set.
Yeah, great, thanks. And we'll put some links in the show notes with more information. Now back to Holly. I asked her what drew her mathematically to the areas of number theory and complex dynamics.
Yeah, I mean, I've always been interested in number theory. For the very basic and I think very common reason that the problems are so easily stated, they seem so fundamental, right? Like, I assume that every person who goes into physics at first wants to understand the universe, right? Like that they want to understand the building blocks, at least, when they're 16 or something like that, and they decide they're interested in it. And similarly, if you're interested in the building blocks of mathematics, to me, that's number theory, right? Like, what can we say about the prime numbers, these sort of multiplicative building blocks of arithmetic? So that's very natural to me, and arithmetic geometry as well, just saying, can we solve polynomial equations, right? Like Fermat's last theorem, I think catches people's interest because it seems so fundamental. And so number theory, I think, is something that is a very easy sell in terms of being interested in, because the questions are very fundamental, but they've been studied for so long that there's a lot of mathematical depth there and a lot of interesting techniques and a lot to learn. Complex dynamics, I think, became interesting to me. I mean, again, in part because I started interacting with people who were interested in complex dynamics that I found very fruitful. But I think also there is an appeal to the field, which is it has a flavor of experimentation. Even though it's a field of pure mathematics, you can sort of draw these wonderful pictures and see maybe what you expect to happen or make predictions about what you think is happening mathematically. And it's motivated by that kind of experimentation in a way that parts of arithmetic geometry, I think, are not. And so I liked the interaction there.
And maybe if we can give a brief glimpse, so complex dynamics, it's about dynamical systems defined by equations.
Yeah, that's right. I mean, so what is a dynamical system at its heart? It's really just a function, right? Like a rule from moving from time 0 to time 1, and then time 1 to time 2, and so on. So we use dynamical systems. We use the maths of dynamical systems to describe, say, orbital mechanics, or, where are all the planets right now, that kind of thing that we're all familiar with. In the more abstract setting, this can be somehow actually much simpler maths in a sense, right? Even just to say, like, I'm taking a complex number and then I'm squaring it, and then I'm squaring it again, and then I'm squaring it again, and what can I understand about what this map does to the complex numbers? It's a very simple question, and indeed that's kind of a simple example, but it is an interesting one.
And I mean, these kind of things that people might be familiar with, like the Mandelbrot set, for example, come from literally quadratic functions.
Yeah, that's right. The most
already...
basic possible ones that, I mean, okay, there are linear functions. They don't have very interesting dynamics. And yeah, that's right. The next simplest case somehow is really fundamental, from which the Mandelbrot set arises.
So the Mandelbrot set is, people might have heard of it as a fractal. There's also things called Julia sets, which are fractals, and they're all very beautiful. Does that add to the appeal of the area, like the pictorial side?
I think so. Not from an aesthetic viewpoint for me. I mean, it's nice to see that the pictures are beautiful, but more from what I was saying about experimentation. That I can really, if I see some phenomenon in front of me in the picture, then try to describe it mathematically, and then even better, prove it mathematically. Then there's something satisfying about it's almost, it feels like an observational science a little bit, in a way that other areas of pure mathematics may not always.
And so this is dynamical systems. You've talked about number theory. So how do those two link up?
Yeah, it's a good question. There's a lot of ways. So let me just describe a couple of the ones that people might be familiar with. I mean, one thing to know, first of all, is that some of the things we're most interested in number theory are secretly dynamical, right? Some more secretly than others. So for example, the Fibonacci sequence, right, which has attracted a lot of interest and still has lots of open questions. Like, here's something we don't know the answer to. Are there infinitely many prime Fibonacci numbers?
Oh, we don't know that.
We don't know the answer to that, right? So the Fibonacci sequence is, of course, dynamically generated, right?
Yeah.
You can think of it as I've got a sequence where I take the last two numbers and add them together to produce the next.
Which is a dynamical
process. And in fact, you can even put it in terms of like a single, you don't have to think about taking the last two if instead you construct a map on like a vector with two elements. You can really just put it into this context of complex dynamics totally cleanly.
Interesting.
So there's that connection of things that we've already been familiar with from number theory having a dynamical interpretation. And then, of course, once you have the dynamical interpretation, you can either say, generalize what you know about Fibonacci to other similar dynamical systems, say, or you can say, hey, I've got all these dynamical tools. Can they tell me anything that the number theoretic tools couldn't? So that latter has been successful also. For example, elliptic curves, which are a very well-studied subject in number theory. They're at the heart of the proof of Fermat's last theorem, for example. They have relationships to cryptography and so on. They come naturally with dynamical systems because one of the key sort of algebraic features of an elliptic curve is you can add points together on elliptic curves. This is why they're powerful, right? They're geometric things which also have algebra and also arithmetic. So the algebra itself of adding a point to another point, that's a dynamical system if you add a point to itself, right? Mm-hmm. So I can take some point on the elliptic curve, I add it to itself, I get another point on the elliptic curve. That's exactly, and then I can repeat the process. That's a dynamical system.
Oh, interesting, yes.
And so a lot of things that you can say or predict about elliptic curves can be directly translated into dynamics. And so that's another point of connection that's been really fruitful.
Okay, that's very interesting. And in your work, generally, is there, like we often ask people that, do you have a favorite mathematical moment? Like, is there something that always springs to your mind when you think about doing maths? Like a moment where you realize something where where you had a eureka moment or maybe something else.
Yeah. No, it does happen. It does happen. Maybe once every 7 years. I mean, I do remember them. I even remember my first one, which I think I've spoken about in public before, which was, I won't go through what the theorem was. Anyways, I was studying for something late in my undergraduate degree, and I was sort of up late trying to understand the proof of this theorem, which is a first theorem in analysis called the Bolzano-Weierstrass theorem. Okay, whatever that is, it's fine. And I had read the proof a few times and of course met it in lectures, and just, it didn't click, right? And at some point, late in the night, it did. And I can't explain to you why. I read it for the 100th time, and suddenly I understood it when I hadn't before. And the thing that is so shocking, and this has also happened in research now a couple of times and so on, but the thing that is shocking is that it's not that you go from like not quite understanding it to kind of understanding it. It's like you go from pitch black to the surface of the sun, right? Like not only do you understand it, but you can't understand how you didn't understand it before.
Yes.
If that makes sense, right?
Yeah.
Like it's so clear all of a sudden that it doesn't make any sense. And this does happen. I mean, this phenomenon does happen in research, but somehow less frequently, because you have to take the time to convince yourself a little bit when you're really working on something new and not an argument that someone else is presenting to you. You have the moment, but it's not quite as certain, I suppose. Sometimes it is, but not as often.
Yeah, and it's not because then when you're doing your own research, you're not just consuming something. You're not just passively trying to understand something.
That's right.
That's
yeah,
different.
and so and you wanna. I mean, if at least I make mistakes all the time, and so you feel like this might be what I need. This might be it. I might understand it now, but then you want to check.
So apart from doing the maths and the research, you're also quite active in communicating it to wider audiences. So, for example, through Numberphile. What do you enjoy about that, and why do you think is it important?
Well, it's important because my friends are impressed when I get recognized in public, of course. No, I'm just kidding. I love talking about maths with other mathematicians. But when you've specialized in something for a long time, you lose a little bit of openness, right? I think people that are interested in understanding mathematics but are not mathematical specialists are more open to learning about the connections between different fields of mathematics. They're more open to new techniques or ideas that they haven't met before, or accepting them, or trying to poke around at why they might be true or not be true. And so they sort of let it fill their brain in a way that mathematicians don't, right? I mean, if I go to a math talk that's aimed towards me, I sort of file it away in my mental filing cabinet of mathematics, like, okay, it's related to this and that and the other thing, and I understand this part and not that part. Instead of just sitting there and sort of appreciating in itself what has been done. And I think so communicating to audiences that are still learning but choosing to immerse themselves in mathematics is somehow satisfying. It's a more receptive audience in some ways. I think also the truth is just that it just is rewarding on the most basic level to have someone tell you, I didn't know this was a thing. I now find it interesting. I want to understand more about it. And this was worth my brain time, right? And so it just feels good to be able to communicate with other people on that level, because I think that, our chances to communicate, well, okay, I don't want to get too philosophical. But the point of life is to communicate with other humans, right?
Yeah.
And our chances to do that are often very limited, for example, to the people that we live in the same town as, or, work with, or something like that. And something that has a big reach, like Numberphile, of interested audience, it's just so valuable to be able to establish that little thread of communication with so many people.
Yeah. And especially if it's about a subject that it's so lovely when you can actually interest somebody in something that they're frightened of.
Yeah, that's right. That's right. Well, and also just to, I think I didn't recognize when I first started doing Numberphile that anyone would want to watch it.
Yes.
Right, because I mean, truthfully, not to make light, but it often happens to me in personal life that I tell someone what I do and it's the end of the conversation, right?
Yes.
Or maybe they say like, I hate maths, or I don't like maths, or I never understood maths, or whatever. And I didn't recognize that there was such an appetite for people to talk to people who are expert mathematicians, but not expert mathematicians in the sense that, I'm going to be totally incomprehensible, but expert mathematicians who actually want to excite other people about what they're doing. And so that was really, it was a surprise to me, but also I'm just really, really grateful for it, right? I mean, it was a happy surprise to me. Yeah.
Yeah. So what would your advice be for younger people who are, thinking about going into research maths?
I would certainly reiterate the advice about thinking about who you work with and not getting so focused on a field of mathematics. I mean, for no other reason, if you're really going to do this for 50 years, you're going to branch out eventually, right? You're not going to stay in the same thing. And it's just so critical who you work with. I think maybe I'll give 2 pieces of advice, which I'm stealing because they're pieces of advice that I got. The first one is that mathematics is a very good career to be a human person in, if that makes sense. I think there's a stereotype that you're shutting yourself up in an office and working frantically 20 hours a day and so on, and it just does not have to be true. It's a career that can involve a lot of flexibility, right? It can involve a lot of travel, and all of that. You have to be willing to move, okay? But a lot of that is stuff that I think people find really valuable right now in terms of trying to balance work and life. The other very good piece of advice I received is that when you are stuck or when you are struggling in your personal life or when your advisor is away for a month and you don't know what to do, the answer is always the same answer, which is keep working. I mean, it sounds so basic, but I think it's really easy. A PhD is so free form, right? Maybe you're lucky you go to some courses for a year or 2 or something like that if you're in the US style PhD. But a lot of the time you're just sitting there. Your job is to sit there and think and occasionally listen to other people talk about mathematics, but usually it's just to sit there and think. And it's just so easy, and it happens to everyone eventually, that you just get sort of paralyzed with, will I ever prove anything? And then once you prove something, you're like, well, will I ever prove enough to write a paper? Oh, well, I've written a paper. Will I ever prove enough to write a thesis? And so every stage you don't know, and you freeze for a little while. Most people, including myself, certainly. And so the only thing you can do at that point is to take those voices in your head, you accept that they're in your head, and you just keep working anyways. So that's my advice.
Good.
Keep working.
Keep working. That's good advice, actually. And it's not one that has come up a lot. That's a new one, actually. So,
well, it can sound quite cold when you're giving it in person, right? If I have a student who comes to me struggling and I say, just keep working, they might not quite feel like I've heard about their struggles, right? But, and I'm not sure I appreciated it when I received that advice, at least not in the moment. But it was actually incredibly useful advice. I think because one of the toughest things about, it's just intellectually difficult to get far in mathematics, right? You have to sit and think deeply for a long time. And so, as I said, everyone's going to get stuck at some point. And one of the things that's really easy to happen and that you really want to avoid is getting somehow circularly stuck, which is not only are you stuck, but then you're beating yourself up for getting stuck, right? And you're questioning yourself and you're going around and around and around this circle of negative thoughts about how hard this all is, right? And you can't stop the first one. You can't stop the first thought that this is hard, because it is hard. But what you can do is you can take that and say, okay, this is hard, and I'm going to carry on anyways.
And there's some faith in that advice, right? That faith in that it will actually, you will become unstuck and something will
That's true. That's true. I suppose the more pessimistic advice that I would also give is that not ending up with a maths PhD, not the end of the world.
That is true. People do live without maths
Not
PhDs.
the end of the world. That's right. I know a lot of people who have stopped being a mathematician at various phases of their career, and who have led very successful and contented lives.
Yes, and there's a lot you can do with your skills as a mathematician.
Yes.
So you said you've been here in Cambridge, so at the Department for Pure Mathematics and Mathematical Statistics for 10 years, nearly 10 years. So what's it like working here?
Oh, it's
what
fantastic.
Like
it's basically the best job a mathematician can have. The quality, the level of seriousness and mathematical depth of the colleagues that I have and the students that I have is, I know it's an overused word, but the right word is inspiring, honestly, right? Like, if you are the kind of person who sort of levels up to where the people around you are, this is a phenomenal place to be. I think that, when people hear Cambridge, Cambridge Maths in particular, they think about ego and intensity, maybe is the right thing to say. And I think that those are both valid things to think about Cambridge Maths. And so, I personally, I sort of thrive in that department. I want my ego to match everybody else's, and I want it to be justified, right? You want to work as well as everybody else does. And so I find it incredibly inspiring, and especially, the shocking thing is the students. There is just, I'm now used to it after 10 years or so, but, comparing my 20-year-old self to these 20-year-old students is really, I just am so impressed every time with how mathematically mature they are, honestly, and how focused they are on what they're doing. So that's really a pleasure, is to teach someone who really cares and wants to learn what you have to teach them. You can't beat that, really.
That was Holly Krieger talking to Marianne here at the Centre for Mathematical Sciences in the University of Cambridge. That's it for this podcast. If you've enjoyed listening, please consider recommending us to a friend or rate and review it wherever you've been listening. Thanks for listening, and bye for now.